In this video, we will look at how to obtain the electric field due to a continuous charge distribution. We assume that you already know how to find the electric field due to a set of discrete point charges. But how do we tackle the case of, say, a charged rod or a charged plane, and so on? In this video, we will specialize in finding the electric field due to a charged straight rod, but the ideas of this video apply even in the cases of other geometries. So, the example we will consider is a thin rod of length L that has a total charge of Q, which is spread uniformly over its length. And we want to find the electric field at point P, which is a distance A above the origin. So the rod is placed on the x-axis. It's going from x equals minus L over 3 to x equals 2L over 3. There's nothing special about these numbers. I just chose them somewhat at random. And we're trying to find the electric field at a point P, which is on the y-axis at a distance A above the x-axis. So how do we approach this problem? Well, we start with what we already know, which is how to find the field due to a point charge. We know that the electric field due to a single point charge is given by E is equal to KQ over R squared times R vector over R. But you would say the rod is not a point charge. But what we can do is chop up the rod into an infinite number of tiny pieces, which are so small that they can each be considered a point charge. So we are going from the electric field due to a single point charge to the electric field due to a small amount of the rod, which will carry a small amount of charge dq and produce a small electric field dE. Once we have that dE due to a single piece, we find out the dE due to another piece and another piece and another piece and so on, and then add up all these electric field vectors to get the total electric field. Of course, in the limit, as the number of pieces go to infinity, this summation will turn into an integration. So to reiterate, what we are doing is taking a situation and chopping up the charge distribution, which is the rod, into tiny pieces. So for example, we take a tiny piece here of length dx and charge dq. All right. Now it's important that when you draw out your picture and draw your little selection, that it should not be at a special point. So it should not be directly below at the origin. It should not be at one of the extreme ends of the rod. It should be at some generic spot, preferably though on the positive side of the axis, regardless of whether that's on the x-axis or y-axis and so on. For now, we are going to just focus on this little piece here with length dx and charge dq. But the idea is that eventually when we move to the integral, what that does is it allows this piece to move from here to here to here to here, and each time is producing a little field dE, and we're going to add up all those contributions to find the total electric field. Now, since the charge is uniformly spread, this ratio dq over dx, right, the charge over the length, should be the same as the total charge over the total length, because it is uniformly spread, because every little bit of the rod has that same ratio compared to any other bit. Right? The charge is not more concentrated on one end compared to the other. So we can say that dq over dx is q over L. So since the ratio dq over dx is q over L, we can rearrange that to dq is equal to q over L times dx. More generally, however, we would say dq is equal to lambda times dx, where lambda is the linear charge density, that is the charge per unit length, and we can see that it would have units of coulombs per meter, right? So coulombs per meter times meters would give you coulombs. In this example, lambda is a constant, Q over L, but in general it can be a function depending on position. So for example, we could have lambda is equal to cx squared. In this example of lambda equals cx squared, lambda, the charge density, would be 0 at x equals 0, but would become greater as you move to either side of the origin. But we will leave that for another example and focus currently on the setup where lambda is just Q over L. To reiterate, we are trying to apply the formula dE is equal to k dq over r squared times r vector over r to this little bit dq over here. So what we want to do is set up an integral, and to do that in terms of the coordinates, which in this case x and y, we will need to express what we can that occurs here in terms of x and y. So we have established a relation for dq. We've said that dq is equal to q over L dx. Now we need to figure out what r and r vector are. So what is the physical picture behind r vector? Well, r vector points from the source charge, the charge which is creating the electric field, to the test point, right? You're examining the electric field at point P, and so that is the test point. So r vector points from the source to the test. So from the source charge dq to the test point P. But remember, a vector is simply a set of instructions of how to get from point A to point B. So in other words, how do I move to get from this point to this point? Well, I will need to go to the left, right? So I need to move in the negative I hat direction. How far? Well, a distance x. And I will need to move in the positive y direction. How far? Well, a distance a. In other words, r is equal to minus x I hat plus a j hat. This is r vector. Continuing, r is equal to minus x I hat plus a j hat, and therefore the magnitude of that vector, which we denote as just r without an arrow on top, is equal to the square root of minus x squared plus a squared, which is square root of x squared plus a squared, because the minus sign goes away when squaring. We return to the point charge formula that we're trying to apply. dE is equal to k dq over r squared times r vector over r, and now we plug in what we know. So first we plug in for dq. We say dq is q over L times dx. We see that the units have not changed, right? This combination still has the units of charge. And next we plug in for r vector and for r. So r becomes square root of x squared plus a squared, r squared becomes x squared plus a squared, and r vector is minus x I hat plus a j hat. We are almost there. All of this can be put together to give us our expression for dE. So k, q, and l are all constants. We keep them out in front. Dx is over here. We have the vector on top, and then in the denominator, these two can be combined into x squared plus a squared raised to 3/2. And all of this is equal to dE vector. So this is the little electric field produced at point P due to that little bit of charge dq. All that's left is adding up the effect of all the little bits of charge. So we write the full electric field is equal to the integral of dE from 0 to E, right? When we have no little pieces, there's no electric field. And when we've accounted for all the little pieces, we have the full electric field E, right? So that's what we get from integrating dE. On this side, what is the integration variable? Well, that is whatever the d is. So this is dx. So we're integrating with respect to x. And what are the limits of x? Well, in our problem setup, x varies from minus L over 3 to 2L over 3, right? X equals minus L over 3 is the leftmost point where dq can be, and x equals 2L over 3 is the rightmost point where dq can be. So we put those there, and we have kq over L dx, this vector, these powers, all of that. And that is it. That is how you set up the integral. As for evaluating it, well, k, q, and L are all constants. We can pull those out, and we can split these into two separate integrals. One would be dx times x over x squared plus a squared raised to 3/2. The other one would be dx times a over x squared plus a squared raised to 3/2. The I hats and j hats are still there, of course, and we could do those integrals. So let us summarize the process of finding the electric field due to a continuous charge distribution. Step 1. If the axes are not already given, set up the axes and label the various points and distances. So in this case, the axes and the setup was given to us. We had the rod, the origin. The rod was lying along the x-axis. The point P was specified. It was along the y-axis at a distance a above the origin. In step 2, what we do is we chop up our charge distribution into many tiny pieces, right? So we chop it up into lots of little tiny pieces, each of them small enough that they can be considered a point charge, so that we can apply what we know of the electric field due to a point charge. And out of these many tiny pieces, we select one generic non-special piece. So I prefer to select my piece on the positive side of the axis. It just makes keeping track of the signs a little bit easier. But I have to be careful not to select a special piece like the piece at the end of the charge distribution or at the origin and so on. So I just selected something randomly here on the positive side of the x-axis where there is charge. And I label it. I have charge dq. It has a small little bit of length, dx. I'm focusing on length because this is charge spread out along a length. If I was focusing on charge spread out across an area, I would cut out a small little bit of area and say it as a charge dq and an area dA. But here we're focusing on length. All right, so I've selected generic dq. I identify the variable of integration. In this case, what it means is that this is just one dq out of many, right? So what variable changes as dq moves around? So right now dq is here, right? But eventually we're going to add up all the contributions. And dq, there'll be this dq, there'll be a dq over here, there'll be dq over here, a dq over here. So what is changing as I move it around? Its position along the x-axis is changing, right? So we are going to take a stab at saying that, okay, x is going to be our variable of integration. And you might need to go back to step 1. You like to choose your axes in such a way that, if possible, you have only the dq moving along only one axis. But if you're dealing with an area, for example, then you will need it along 2 axes and so on. But yes, you try to adapt your axes to the problem. And sometimes you might use different coordinate systems depending upon the problem that you're interested in. All right, so we've identified x as our variable of integration. And then the last thing is we want to draw R. So R, remember, points from the source of the electric field to the point where the field is being evaluated. In step 3, we will relate dq, position of dq, and R to the variable of integration. So we identified x as the variable of integration. Right, x is what changes as dq moves around. So let's relate all these things to x so that we can turn this from a physical problem into a mathematical problem. which is simply an integral with respect to x. So we see that we have, well, dq is lambda times dx, right? So since this is charge spread along a length, we end up dealing with the linear charge density, lambda, which has units of charge over length. And so we relate dq to dx. So this turns it from a problem of adding up charges to a problem of adding up little lengths, dx. We relate r to x and various other constants. So r, remember, points from the source to the test point. So we need to move in the negative I hat direction, and it's a distance x, so we write minus x I hat. And we need to move in the positive j hat direction, distance a, so we write plus a j hat. So that in total gives us r is equal to minus x I hat plus a j hat. This is r vector. And then we find the magnitude of r vector, which we just call r, and that ends up being square root of x squared plus a squared. I want to emphasize a step which I kind of glossed over, which is that the position of dq is it's a distance x from the origin. Right? So again, as our dq varies, we can see that x is going to vary, and so that's how we picked out x as our variable of integration. In step 4, we are going to write the formula for dE and plug in for dq and r. So let's remind ourselves again of the physical aspect of the problem. We have this generic little infinitesimal piece of charge, dq, and it's small enough it can act like a point charge, and it's creating an electric field at this point P. So let me draw an electric field vector at point P. Assuming dq is positive, then the electric field at this point will point away from the positive charge along the line joining them. So it's going to be parallel to the r vector and pointing away from dq. So let me just draw. This is our little dE. As this process continues, when we get to the integration step, what's going to happen is dq is going to move along this charge distribution. So at some point we'll look at a dq over here, which will have its own r, cross out that a to avoid confusion, and it will have its own dE, and now this dE will be again pointing away from dq. It will be a little bit stronger since it's closer, the dq is closer to point P. And so as we do the integration, each dq will contribute a little dE, and we are going to get an infinite number of these little vectors, dE vectors, and some of them we're going to and so we will get an infinite number of these dE vectors, and we will add up all these vectors, and we will see that some of the components will cancel, some of them will add up, and we will get some total overall electric field vector. Right, so that is what is physically underlying this mathematical process. So I just wanted to remind you of that, but for now the step is write the formula for dE and plug in for dq and r. So we write the formula for dE. It's very similar to the point charge formula, except instead of a generic q, we have a dq over here, and we have a dE over here, because each little bit of charge dq will produce a little bit of electric field. And now we plug in for dq, we plug in lambda dx, we plug in for r vector, minus x I hat plus a j hat, and we plug in for r. One thing to check is lambda constant? In this particular problem, lambda was constant because we were told the charge was uniformly spread, but in general, lambda could be a function of x or y, or whichever variable you're considering, and that is something to keep track of. We simplify this, gather together like terms, and the denominator simplifies to x squared plus a squared raised to 3/2. And now step 5. we set up the integral using the appropriate limits. So we identified the variable of integration as x, but does dq move everywhere along x? Does it go from minus infinity to plus infinity? Or does it have bounds? So in this case, we see that, well, dq can move all the way up till here, where x is equal to minus L over 3, and all the way up till here, where x is equal to 2L over 3. So we add up all those tiny electric fields, right? So we're integrating the dE from 0 to E. When there were no little pieces, we had 0 electric field. When we had all the pieces and added up all the contributions, we get the total electric field E. And on this side, our variable of integration is x. So we look at how x changes as dq moves around. And we see that, well, one limit of x is x equals minus L over 3, and the other limit is x equals 2L over 3. And all this is inside the integral. If some terms are constants, we can pull them out. So k is a constant, we can pull it out. In this problem, lambda is a constant, so we can pull it out. But in general, that might not be true. And everything else would stay inside the integral. And remember, this is actually two integrals. The I hat and j hat don't combine, they stay separate. So we could do those two integrals separately. We could have one integral which is this, and another integral which is this. And we could look at those separately. And most of the time in this course, we will just ask you to stop at setting up the integral. But sometimes you, especially in homework, you will need to go on to step 6 and just evaluate the integral. All right, and that summarizes the process for finding the electric field due to a continuous charge distribution.